Describe interaction in process loops. Single loop versus multivariable loop. Single loop control involves controlling a single process variable with a single controller and actuator. This type of control is straightforward and does not involve interaction between multiple loops. Multivariable loop control involves multiple process variables that interact with each other. Controlling these variables requires coordinating multiple controllers and actuators to manage the interactions effectively. Multivariable process. Multivariable process, a process with multiple inputs and outputs where the control actions on one variable can affect other variables. Understanding the interactions in such processes is crucial for effective control. Examples of interacting processes. Simultaneous control of pressure and flow. Managing both pressure and flow in a system can lead to interaction, where changes in one variable affect the other. Controllers must be coordinated to handle this interaction. Blending system example. In a blending system, the control of ingredient flows can interact, impacting the final blend composition. Controllers need to account for these interactions to maintain the desired blend. Flow and pressure control example. Similar to the simultaneous control example, maintaining both flow and pressure requires managing the interaction between these variables. Level and pressure control example. Controlling the level in a tank while also maintaining pressure can be challenging due to the interaction between these variables. Proper tuning and coordination are required. Distillation control example. Distillation processes involve multiple interacting variables, such as temperature, pressure, and composition. Effective control requires managing these interactions to ensure optimal separation. Relative gain analysis. Steady-state open-loop gain for a single loop. Single loop gain, the ratio of the change in the output variable to the change in the input variable in a single loop control system. This gain helps in understanding the system's response to control actions. Steady-state open-loop gain for multiple loops. Multiple loop gain extends the concept of gain to multivariable systems, considering the interaction between multiple input and output variables. This analysis helps in understanding the overall system behavior. Closed loop gain. Closed loop gain. The gain of the system when feedback control is applied. This gain reflects the system's behavior under closed loop conditions, accounting for controller actions and interactions. Relative gain. Relative gain, a measure of the interaction between control loops, defined as the ratio of the open loop gain to the closed loop gain. It helps in determining the degree of interaction and the impact of one control loop on another. Relative gain array, RGA, a matrix that quantifies the relative gains for a multivariable control system. It provides insight into the interactions between control loops and helps in designing control strategies. Properties of RGA includes properties such as the sum of each row and column being equal to 1, and the ability to identify loop interactions and pairing strategies. These sections provide a comprehensive overview of interaction in process loops and relative gain analysis, emphasizing the importance of understanding and managing interactions in multivariable control systems to achieve effective and stable control. Calculating relative gains. Process test method. Process test method. This method involves conducting step tests on the process to observe the changes in output variables in response to changes in input variables. By analyzing these responses, the steady-state gains for the process can be determined, which are used to calculate relative gains. Math model or ratio method. Math model or ratio method. This approach uses mathematical models of the process to calculate relative gains. The models represent the relationships between input and output variables, allowing for the computation of relative gains without physical testing. All loops open method. All loops open method. In this method, all control loops are kept open while step changes are introduced to one input at a time. The resulting changes in all outputs are measured, and the relative gains are calculated based on these open loop responses. The matrix method. The matrix method, a mathematical approach to calculate relative gains using matrix operations. This method involves constructing a gain matrix from the process model and performing matrix manipulations to derive the relative gain array, RGA. 3x3 systems. Example of applying the matrix method to a 3x3 system, illustrating the process of calculating relative gains for more complex multivariable systems. Assigning loops to minimize interaction. Loop assignments. Loop assignments, the process of pairing input and output variables in a way that minimizes interaction and optimizes control performance. Proper loop assignment is crucial for effective multivariable control. Example of Lula in the 0 to 1 range. An example showing how to assign loops when the relative gain number lever is within the 0 to 1 range, indicating minimal interaction. Example of process with letter outside the 0 to 1 range. An example demonstrating loop assignment for processes where leg load is outside the 0 to 1 range, requiring more careful consideration to minimize interaction. Dynamic considerations in interacting loops. Dynamic considerations. Factors such as time delays, response times, and dynamic behavior of the process that influence the effectiveness of loop assignments. Understanding these dynamics is essential for minimizing interaction and achieving stable control. Tuning. Tuning, the process of adjusting controller parameters to achieve the desired control performance. In multivariable systems, tuning must consider the interactions between loops to avoid destabilizing the process. Designing the process to minimize interaction. Designing the process. Strategies for designing process systems to inherently minimize interaction between control loops. This can include layout considerations, process modifications, and selecting appropriate control strategies to reduce the potential for interaction. These sections provide detailed guidance on calculating relative gains, assigning control loops to minimize interaction, and considering dynamic factors in the design and tuning of multivariable control systems. Determine where decoupling is applicable. Definition of decoupling. Decoupling, the process of designing control strategies to minimize the interaction between control loops. Decoupling aims to ensure that each control loop operates independently, reducing the effect of changes in one loop on others. Decoupling examples. Full decoupling example. An example illustrating the application of full decoupling, where control strategies are designed to completely eliminate interaction between loops. This involves using decouplers to compensate for the interactions, resulting in independent loop operation. Partial decoupling. An example demonstrating partial decoupling, where interactions are minimized, but not entirely eliminated. This approach reduces the complexity of full decoupling while still improving control performance. Determine applicability of dynamic matrix control, DMC, to multivariable control problems. Introduction to DMC. An overview of dynamic matrix control, a model-based control strategy used for multivariable control problems. DMC uses a dynamic model of the process to predict future behavior and optimize control actions. Definition of DMC. Definition of DMC, a detailed explanation of dynamic matrix control, including its principles and operation. DMC is characterized by its use of a dynamic process model and optimization techniques to manage multivariable control systems. Historical perspective. Historical perspective, the development and evolution of dynamic matrix control, highlighting key milestones and advancements in the technology. Why is DMC an attractive alternative? Why DMC is attractive. Reasons why DMC is considered a valuable alternative for multivariable control, including its ability to handle complex interactions, optimize control performance, and manage constraints effectively. Different commercial versions. DMCC version, a specific version of dynamic matrix control developed by DMCC, highlighting its unique features and applications. Honeywell version, the Honeywell implementation of DMC, detailing its capabilities and use cases. IHUN version, the IDCOM version of DMC, including its specific characteristics and industry applications. Other versions of DMC. Overview of other commercial versions of DMC available in the market, each with its own features and advantages. DMC theory, linked to classical control theory, the relationship between DMC and classical control theory, explaining how DMC extends traditional control concepts to multivariable systems. The general DMC model equations, the fundamental equations that underpin dynamic matrix control, used to predict process behavior and calculate control actions. Calculating the correct control response, the process of determining the appropriate control actions using DMC based on the dynamic model and optimization criteria. How the DMC controller algorithm optimizer functions, an explanation of how the DMC algorithm works, including its optimization process and decision-making criteria. Application of DMC technology. Planning the DMC application. Steps for planning and preparing a DMC implementation, including defining objectives, selecting processes, and designing control strategies. The pre-test, conducting preliminary tests to gather data and validate the DMC model before full implementation. Tuning, fix-up, economic justification. The process of tuning the DMC controller, making necessary adjustments, and justifying the economic benefits of the DMC implementation. The full plant test, executing a comprehensive test of the DMC system in a real plant environment to ensure its effectiveness and reliability. Model development, controller development, initial controller tuning, the stages of developing the DMC model, designing the controller, and performing initial tuning to achieve desired performance. Implementation, final tuning, operator training, steps for implementing the DMC system, performing final tuning adjustments, and training operators to use the new control system effectively. Applicability criteria, good DCS in place, ensuring a robust distributed control system DCS is available to support the DMC implementation. Linear or linearizable processes. DMC is most effective for processes that are linear or can be linearized. Multiple manipulated variables, ideal for processes with multiple inputs that need coordinated control. Interactions between controlled and/or constraint variables. DMC is suitable for managing interactions between variables, enhancing overall control performance. Constraints, the ability of DMC to handle process constraints, ensuring operations remain within safe and optimal limits. Slow processes. DMC is particularly effective for processes with slow dynamics, where predictive control can significantly improve performance. Binary distillation process. Application of DMC in binary distillation processes, managing multiple variables to optimize separation efficiency. Three-product distillation process, use of DMC in three-product distillation processes, coordinating control actions to achieve desired product specifications. These sections provide detailed information on decoupling strategies to minimize interaction in multivariable control systems, and the applicability of dynamic matrix control, DMC, for solving complex multivariable control problems, including its theory, implementation, and practical applications. Tash describing feed-forward control. Summary of feedback. Feedback loop advantages. Feedback control automatically corrects deviations from the set point by adjusting the control variable based on the error signal. It is simple to implement and effective for maintaining the desired output in the presence of disturbances. Feedback loop disadvantages. Feedback control reacts to errors after they occur, which can result in time delays and oscillations. It may not prevent disturbances from affecting the process before correction, leading to temporary deviations from the set point. Simplified feed-forward scheme. Simplified feed-forward scheme. Feed-forward control anticipates disturbances by measuring the disturbance variable and adjusting the control variable proactively. This preemptive approach aims to prevent disturbances from affecting the process, enhancing stability and response time. Advantages and limitations of feed-forward control. Feed-forward advantages. Feed-forward control provides a faster response to disturbances, reduces process variability, and can improve overall control performance. It addresses disturbances before they affect the process, minimizing error and enhancing stability. Feed-forward disadvantages. Feed-forward control requires accurate measurement and modeling of disturbances, which can be complex and costly. It may not be effective if the disturbance model is inaccurate or if unmeasured disturbances occur. Feedback trim loops. Combining feed-forward and feedback control trim loop provides a comprehensive control strategy. The feed-forward loop handles anticipated disturbances, while the feedback loop corrects any remaining errors, ensuring robust and accurate control. Tash describing specific mass flow feed-forward applications. Mass flow processes. Mass flow processes describes processes where the primary control variable is the mass flow rate. Feed-forward control can be applied to manage disturbances affecting the mass flow, ensuring stable and efficient process operation. Level tank application. Level tank application. An example of a feed-forward control system applied to a level tank. The feed-forward loop adjusts the inflow based on changes in the outflow or disturbances, maintaining the desired tank level. Applying feedback trim loop to tank level application. Feedback trim loop for tank level enhances the level tank application by adding a feedback trim loop. This combination ensures precise control by correcting any deviations not addressed by the feed-forward loop. Single element drum level application. Single element drum level, a basic feed-forward control application where the feed-forward loop adjusts the drum level based on single element measurements, such as steam flow. Two-element feed-forward drum level application. Two-element feed-forward drum level involves two measurements, steam flow and feed water flow, to improve control accuracy. The feed-forward loop adjusts the feed water flow based on changes in steam flow. Three-element feed-forward drum level application. Three-element feed-forward drum level uses three measurements, steam flow, feed water flow, and drum level, for optimal control. The feed-forward loop adjusts the feed water flow based on both steam flow and drum level changes, providing the highest accuracy and stability. These sections provide a comprehensive overview of feed-forward control, its advantages and limitations, and specific applications in mass flow processes, particularly focusing on level tank and drum level control systems. Describing specific energy flow feed-forward applications. Simple energy flow example. Simple energy flow example demonstrates the application of feed-forward control to a basic energy flow process. The feed-forward control loop adjusts the control variable based on anticipated disturbances, such as changes in the energy supply, to maintain a stable process. Heat exchanger energy flow example. Heat exchanger energy flow, application of feed-forward control in a heat exchanger system. The feed-forward loop adjusts the flow rate of the heating or cooling medium in response to changes in the inlet temperature or other disturbances, ensuring the desired outlet temperature. Implementing the feed-forward model. Implementing the feed-forward model. Steps involved in developing and implementing a feed-forward control model. This includes identifying disturbances, measuring their impact on the process, and designing the control adjustments needed to counteract these disturbances effectively. Applying a feedback trim loop to the feed-forward. Feedback trim loop application. Feedback trim loop application describes the process of integrating a feedback trim loop with the feed-forward control system. This combination allows for fine-tuning of the control output, ensuring that any residual errors not addressed by the feed-forward loop are corrected by the feedback loop. Applying dynamic compensation to feed-forward. Testing the feed-forward system. Testing the feed-forward system. Procedures for testing the feed-forward control system to verify its effectiveness. This involves introducing disturbances and observing the system's response to ensure the feed-forward model correctly predicts and compensates for these disturbances. Adjusting dynamic compensators. Adjusting dynamic compensators. Methods for tuning dynamic compensators within the feed-forward control loop. Proper adjustment of these compensators ensures that the feed-forward control system can accurately predict and respond to dynamic changes in the process, enhancing overall stability and performance. Scaling the feed-forward calculation. Example of scaling the heat exchanger. Scaling the heat exchanger. An example illustrating how to scale the feed-forward calculations for a heat exchanger. This involves adjusting the feed-forward model to account for different operating conditions or changes in process parameters, ensuring accurate control. Scaling in digital applications. Scaling in digital applications discusses the principles and techniques for scaling feed-forward control calculations in digital control systems. This includes considerations for data acquisition, processing, and implementation in digital controllers, ensuring the feed-forward control remains effective across various digital platforms. These sections provide comprehensive guidance on specific energy flow feed-forward applications, integrating feedback trim loops, applying dynamic compensation, and scaling feed-forward calculations to maintain effective and stable control in different process scenarios. Starting up a feed-forward scheme. Starting up a feed-forward scheme. Starting up a feed-forward scheme, detailed steps for initiating a feed-forward control system. This includes initial setup, calibration, testing, and verification procedures to ensure the feed-forward control scheme operates correctly from the outset. Emphasizes the importance of systematic checks and adjustments to optimize performance and stability. Applying a ratio control scheme. Simple ratio example. Simple ratio example illustrating the basics of ratio control. Ratio control maintains a fixed relationship between two process variables, such as flow rates of different streams, ensuring consistent process operation. Ratio controller application. Ratio controller application explains how to implement ratio control in various industrial applications. This section covers the selection of ratio control configurations, tuning of ratio controllers, and the integration of ratio control into existing control systems to achieve desired process outcomes. Adding feedback trim. Adding feedback trim describes the enhancement of ratio control schemes with a feedback trim loop. This combination allows for more precise control by correcting any deviations from the desired ratio, ensuring the control system responds effectively to disturbances and maintains the specified ratio accurately. These sections provide detailed instructions on starting up feed-forward control schemes and applying ratio control schemes, highlighting practical steps and considerations for effective implementation and optimization in industrial processes.